Hola, soy Alejandro McDonough, Managing Director de Wärtsilä Chile. En nombre de Wärtsilä, quiero darles la bienvenida a este webinar en el que presentaremos nuestra visión acerca de la transición energética en Chile, un camino hacia la carbono neutralidad, cómo descarbonizar la matriz eléctrica en forma eficiente, segura y económica. Wärtsilä tiene un propósito que es habilitar el desarrollo de sociedades sustentables mediante tecnología. Como proveedores en las industrias marítimas y de energía, desarrollamos e implementamos soluciones orientadas a minimizar el impacto en el medio ambiente. En el ámbito de energía eléctrica, hemos estudiado y modelado más de 150 sistemas a lo largo del mundo. El aprendizaje de esos estudios se encuentra comprendido en el estudio del caso chileno. Esta es la tercera versión del estudio del sistema chileno. En esta ocasión, hemos ampliado el alcance más allá de analizar el desarrollo óptimo de la matriz de generación, retirando carbón y diésel. En este estudio, tratamos también los requerimientos de seguridad y estabilidad que surgen a partir del retiro de la generación en base a carbón. Y hemos esbozado sugerencias de cuáles serían medidas, regulaciones a desarrollar para viabilizar las inversiones necesarias para incorporar flexibilidad y seguridad al sistema. Quiero presentar a nuestro equipo: Silvia Zumaraga, General Manager de Market Development para Latinoamérica y Caribe; Anania Saraf, Power System Analyst; Stefan Schleg, General Manager de Power Systems; Alex Espejo, Senior Market and Financial Analyst; y Jussi Heikkinen, Director de Grow and Development. Un agradecimiento especial a nuestra moderadora, directora ejecutiva de Acera, y nuestra muy querida amiga Analía Rojas.
Hello to you all. In 2023, non-conventional renewable plants had a record participation in the Chilean electric system of 36.7%, while the contribution on electricity generated with thermal sources was 37.3%. In Chile, we have an installed generation capacity of 35.4 gigawatts, including hydroelectricity, thermal, and non-conventional renewable energy, and a very discrete figures in storage. To the extent that thermoelectric plants have been removed from the system, operational requirements will be generated that must be satisfied. So here are questions related to the increased penetration of the non-conventional renewable energy that Chile has been experimenting since 2015 and on for its electrical matrix. In this context, the discussion regarding market designs, reforms, and the operation of an electrical system with high penetration of renewable energy is being held in such a way that is necessary some incentives existing to develop new projects that allow decarbonization to materialize. So for that reason, I'm very happy to have the Wärtsilä team here to talk about the latest study that Wärtsilä has developed for Chile for our electrical system. In this context, I would like to open the discussion, this talk, with Silvia to address some questions that are probably very interesting to focus on the first part of this discussion. Silvia, how are you? I would like to ask you, how would you describe the situation in Chile in your view?
Well, Analia, Chile has been blessed with an enormous wind and solar resources, and it has been at the front of incorporating all those resources into the power system up to now. However, it seems that the system has reached a limit, and with the graphic that I'm showing, I try to illustrate the situation and the root cause of this problem. We see major curtailment, renewable projects financially struggling, and although there is a very ambitious retirement coal power plant program, the inflexibility of the system, along with some delays in transmission, are causing that Chile is now perhaps at a dead end or at a road cross. the market seems to be falling short of nations' expectations. And you see that there is no space for more renewables. Emissions are not decreasing at the pace expected or needed, increasing side payments due to the fact that coal power plants must keep running. So the situation is serious, and it requires that the system, a system-wide approach, and some actions must be taken as soon as possible.
Yes.
So let's take a look at the severity of the situation and some tangible facts. We see that renewable curtailment is increasing. Look at some of the figures. In 2023, the curtailment was 7%. And we anticipate that the curtailment for 2026 will be around 17%. So, which means that the new generation added between the periods of 2024 and 2026 would have a curtail rate of 30%. So that is quite significant. On the right, I also showing that the system is being hit with a huge amount of side payments, and that we can see the trend that has been increasing, especially a big jump between 2021 and 2023. So despite adding renewables, emissions are not declining significantly until more coal power plants are retired. Side payments will continue growing unless coal power plants are retired. So the fact is, we have to act now, or the trend will continue up. In this slide, I try to represent the system flexibility limitations that it has been increasing due to adding renewables along with some other issues. But we can compare 2017 and 2023, and the graph shows how the coal power plants were operating during 2017 in comparison with 2023. And we still see that coal power plants remain in the system. So although Chile has been adding a large amount of renewables, I believe that Chile is missing an integration plan which will allow to make room for more renewables. To do so, they need to be able to close the coal power plants in a reliable way. However, today, these power plants have a vital function providing firm dispatchable capacity at nighttime, along with inertia, frequency, and voltage control, plus short circuit capacity. These coal power plants cannot stop for the day, and they need to remain in the system, and therefore they are causing the situation that we saw where some of the renewables are going on a struggle financially, but at the same time, side payments are being increased, as I mentioned before. So essentially, Chile is facing the fact that important decisions must be taken now in relatively fast. So again, without too many words, the picture is an illustration of what I believe Chile is facing. End of the road. Do we go one way or we go to a separate way? And I think my colleagues and I, we will try to go through a roadmap in which Chile must be able to close the coal power plants in a reliable way and reach to the targets of full descarbonization pathway.
Thanks, Sylvia. Very interesting. And let me have a second question for you, because you mentioned some issues that are clearly part of what you may describe as a crisis, right? So how do we get out of that crisis? What is the proposal? How do you see to solve in the very short run, but also in the long term?
So before that, let me share with you that a few months ago, our team conducted a study utilizing a software called Plexus, which is an optimization software. And we modeled the system in two stages. The first stage was a short-term stage a period until 2026, and the second period was until 2032. So we will share with you these two stages and what the system has to address in each of these periods. So like we said before, Chile has had this ambitious target to close the coal. However, our study shows that they could even do it in an accelerated way. So the first results show that Chile could close 2.5 gigawatts of coal, reduce curtailment, saving between $300 and $500 million on those side payments that we spoke in the previous question, and they could lower carbon emissions significantly while making room or space for the renewables. So how to do it and what would be the enablers that would allow to retire these 2.5 gigawatts of coal? Storage and firm flexible gas power, plus adequation of auxiliary service has to be taken into consideration. So it's critically that we ensure the adequate capacity of fast starting and firm gas capacity to fill the energy gaps and continuously providing the security of supply. Storage by itself has its limitation, and we will get into more of details. So therefore, along with the storage that we agree must be present, we will need to add around 240 megawatts of firm flexible power plants, allowing the system to be robust and ready to be able to retire this amount of coal, the 2.5 gigawatts. That way, we will be making room for renewables. Another thing that to notice is that those current gas assets that Chile has in the system will be also optimized, and they will be utilized at the time that is needed, and they will come to the rescue, and therefore the coal power plants will be displaced at night by the gas assets that you have in the system today. So let's take a look at the benefits. So if you follow the first recommendation between this period of time, you will see benefits. So we try to compare a system roadmap as it is, the current plan that we understand Chile is following today, versus the proposed accelerated plan that we discussed a few minutes ago. And we see clearly benefits. There are three major benefits that we will see in the Chile power system. And those three will be: curtailment of renewables will be reduced. We can compare that under the current plan around 17%, but following these recommendations, the curtailment will be around 7%. Another major benefit is in the CO2 emissions, and we see that Chile could reduce more than double the megatons. And the third benefit that is immediately noticeable in our modeling is the system variable cost reduction. So following this plan, Chile could be back on track for this 100% decarbonization roadmap.
Thank you very much, Sylvia. So let's move to the next part of the questions to Anania, because regarding what Sylvia has already described, and once you're back on track, so which is the view of what is the next step? Mainly because we need to move forward and to have a prioritization in terms of the next step that is important for, obviously, the fact that this system is transforming?
Thank you for the question. For Chile, the next step would be to pursue decarbonization. As Sylvia mentioned earlier, we utilized power system modeling to create a capacity expansion model for Chile over the short term until 2026, as well as over a longer horizon. The objective of the long-term model was to understand the necessary actions required to achieve net zero in Chile by 2032. That is, in the next 10 years. We explained that in the short term, until 2026, the retirement of around 2,500 megawatts of coal power would be possible through building a combination of firm, flexible gas power and battery energy storage. Although this is imperative to relieve the ongoing challenges faced by the Chilean power system, it is also crucial to carry out the retirement of all inflexible thermal power assets at an aggressive pace. Through our model, we see that the complete retirement of coal and diesel capacity is possible in Chile by 2030. This is enabled by building around 6,600 megawatts of renewables, which includes wind and solar, and around 900 megawatts of additional battery energy storage. After this stage, a full phase out of fossil fuels can be achieved by converting the newly built flexible firm capacity as well as the existing gas assets in Chile to run on sustainable fuels by the end of the decade. It is important here to note that there is no silver bullet when it comes to decarbonization, and it's about a combination of technologies that will enable renewable growth and maintain reliability in the system.
Okay, thanks, Anania. So, in your view, why does Chile need gas? Because we know that energy storage is already there, and there's a bunch of renewable projects also under construction, already operating. In fact, is the most important capacity that we have right now in the system. So, why is it that Chile needs gas?
That's a very valid question. So, energy storage and engines essentially perform different roles in supporting renewable integration in power systems. High renewable grids require balancing on multiple levels. So, this ranges from on a second, minute, intraday level, as well as to a seasonal level. Where battery energy storage is superior is in balancing on a second level, providing very fast response to fluctuations on the grid. However, the technology is usually limited to intraday balancing due to the high energy-related costs associated with battery energy storage. Here is where flexible gas power plants can strengthen the grid by providing dispatchable power over longer durations, which is crucial especially during nighttime where solar is unavailable, and also generally to overcome unexpected weather patterns over the year. Thus, during decarbonization, the combination of renewable and storage on their own will not be efficient to meet power demand 24/7, unless reinforced by firm, flexible, dispatchable capacity. We studied this further by modeling two scenarios for a net zero pathway for Chile. One in which net zero is achieved only through building storage and renewables, and one where storage and renewables are also supported by flexible firm gas capacity. Although both systems are carbon neutral, the system without thermal costs 27% more to build in terms of capital cost as compared to the Wärtsilä system, and it is also 10 gigawatts more in terms of installed capacity, signaling that a system solely based on renewables and storage is not cost optimal.
Many thanks, Anania. In fact, how do you see, or what is your view on why is this firm flexible generation different from the combined cycle gas turbines that we already have as installed capacity in the electrical system in Chile?
Yes, it is different. So the firm flexible capacity that we refer to here is engine power plants. Although combined cycles are a big improvement over coal, Chile's renewable profile will require gas plants to stop and start multiple times a day. If CCGTs were utilized in that way, it would degrade the plants over time, causing excessive maintenance and start cost. Here is a graph illustrating what 1 week of dispatch for the Chilean power system would look like in 2030, where coal and diesel plants have been completely retired. It is clear to see that engines that provide flexible firm capacity are utilized more often in the system. This is because they can provide fast starting capacity at a cost with no minimum up and down time. They are also capable of running on low loads with a high efficiency, which is vital in a renewables dominated system. Thus, overall, engines offer multiple starts a day without inflicting extra cost to consumers. Lastly, it is evident that inflexible gas is mainly utilized here at nighttime to meet demand surges where solar is limited. It is important, but it does not offer the level of flexibility that engines are able to.
Okay, thank you very much for
Thank you.
this first discussion and dialogue on the matters we have just reviewed. Now I'm going to move to Stefan to continue with questions, but more related to stability and balance of the system. In relation to this subject, transitioning to a more renewable base will surely impact the stability of the system. That's what we have seen as a discussion in other markets and also in other systems. Can you elaborate on how it will be impacted and tell us if this stability of the system will be compromised? Is it a matter that we have to address in this short run as a matter of discussion and probably as a matter of technical transformations for the system?
Thank you, Analia, for the question. Well, there are three areas of stability and reliability that are of concern when we see an increase of renewables in the system. The first one is frequency stability, and there we see that we will get a reduced amount of inertia in the system. Frequency stability is about the balance of the load and the generation in the power system, and it indicates if there is an imbalance. The inertia is a property that helps or resists the change of the frequency. This means that if there is a load change, the frequency will move slowly and you have time to react on it. Taking away the inertia, you will have less time to react on it, and you need to have much more or faster controller for that. Next topic of concern is voltage stability, and especially the decreased short circuit capacity. Voltage stability is about, or the ability to maintain steady acceptable voltage in the whole power system. Especially in these cases when you have a disturbance in the power system, or maybe a rapid load increase somewhere or something, you will create imbalance in the voltage. And this picture is indicating how this works. That consider that you have rope hanging in the roof, and this is the strength of this rope varies in different sections. And now you hang on a load. At some point, this will hold. At some point, this will break. And this will then create a ripple throughout the whole rope. And that can cascade into a failure of the power system. And this is what is happening when you introduce renewables, that you get less ability to handle these changes. The last part is restoration capability. For example, it is basically inevitable that you will avoid a grid failure. There are always risks that it can handle, like for example in Japan, there was an earthquake, and this created a failure in the interconnection. And this took them 45 hours to recover. And it is important, very important, that there is a solid grid restoration plan, and this is changing with the introduction of more renewables in the system. When it comes to inertia and how that contributes from different technologies, well, if we start with the conventional solutions like synchronous generators or synchronous condensers, these are generators that are directly connected to the grid, and they provide a mass and support with this resistant to the frequency change. The inverter-based solution that is now coming, they are basically taking away this mass, and they need to be very fast acting instead. The important thing with inertia, there are today technologies that or solutions available to overcome this. First one is, of course, to utilize the synchronous generators that you have installed, install synchronous condensers. But with battery storage, there are also solutions called grid forming mode or synthetic inertia. And these are very fast acting controller that detects if the frequency is changing quickly, and it will then put out the power or reduce the power very quickly. So when it comes to inertia, there are technologies available today. It's just important to be aware of this when looking for the new design of the power system. When it comes to short circuit capacity, well, here there is a big difference between the synchronous generators and condensers and the inverter-based solutions. With synchronous condensers, there you have the capability to actually overload your generator in a very, very short moment. And that is what short circuit capacity is about, that you need to be able to draw a lot of energy or a lot of power on a very, very short moment. And here, typical when we talk about these technologies, it's like 6 to 12 times the rated capacity, depending on the design. On the inverter-based solution, on the other hand, here you have some challenges with that. You have power electronics, and these cannot be overloaded. So they have a protection in itself of, normally 1.5 rated capacity. And that means that it will limit the output from these inverter-based solutions to 1.5, and just to protect themselves. So here we see definitely that synchronous generators and condensers are superior to the inverter-based solutions when it comes to providing short circuit capacity. Then the last part that I was talking about, the restoration plan. This becomes very important, especially when you have a lot of renewables in the system, because renewables are not suitable for the restoration of the power system. When you have a blackout, you need to have firm, reliable power that you can control, that you don't have with the renewables. When it comes to the batteries, well, these are, yes, they can provide some support, but you never know really in which state of charge they are, when this is happening. You don't know how long the blackout will be and when you can charge the batteries again. So yeah, they can be utilized, but to normally to a limited extent because of their limited capacity. So here it's really important to have fast starting and firm power that are dispatchable to use to recover the whole system.
Thanks, Stefan. As a matter of fact, Chile has already begun planning synchronous condenser auctions. And my question here is, how can this firm, flexible gas generation capacity bring additional value to the system? What is your view on that?
Okay. Thanks for the question. Well, if you remember the firm, flexible power plants that we were talking about earlier, here we have the possibility to actually utilize this for full balancing capability. If you consider this engine that we have here, here you can have, to the left, you have the generator, and to the right, you have the prime mover or the engine. And you can place a clutch between these. And this makes you to really fully utilize these power plants. So for example, in the case when you have sun is shining, the wind is blowing, a lot of renewables in the system, you only want the generator to be connected and act as a synchronous condenser. And it will provide the inertia that we were talking about. It will provide the short circuit capacity. But then in those cases when cloud is covering the sun or you don't have any wind, well, then you connect the clutch or on the engine to the generator, and it will then act, to provide power. It will also provide short circuit capacity to the system, and this also makes you actually have a source for the restoration plan if something would happen. So this is the optimal way of actually utilizing your assets to the fullest.
Thanks a lot, of Stefan, for all the matters and issues that you have just touched. I'm going to move right now to a next part, which is obviously part of the interesting conversation, but also which is part of the probably the most important part of the market design that has to do with institutions and authorities that are managing the transformation of electrical system. So we're going to talk about market design, tariffs, regulation challenges, also to see how all these transformations are going to be paid or remunerated. So in this sense, Alex, how do you think, or what are the challenges from the market point of view? Do you think there are problems specific to Chile, or if this is a matter that is part of the discussion and it's present in other markets? How do other markets have dealt with it? Probably there are a lot of experience already in this matter. So let's talk a little bit about that.
Okay. Thank you, Analia, for the question. The rapid growth in renewables has changed the market situation. The variable energy forces a need for flexible and dispatchable energy that existing generation will struggle to provide. This is visible in the price growth of side payments, where the blue and green sections represent assets or generators being compensated to provide ancillary services according to their opportunity cost to provide those ancillary services. These extra costs challenge new renewable projects by inflicting extra costs onto new generators. To compound this issue, our modeling still projects that nearly 8,000 gigawatt hours of renewable energy curtailment will be occurring in 2026 based on the current project pipeline. This is after the addition of over 10 gigawatt hours of battery storage as well. This represents a very large quantity of energy that will be paid $0 per megawatt hour. These two issues force the question of how does Chile continue the growth in renewable generation while keeping these projects diverse and profitable? If Chile wants to continue its decline in emissions, coal must retire, and more importantly, the services it provides must be replaced. Storage and independent synchronous condensers will help address both issues mentioned before, but they will not solve them in the short term. These services are late night energy demand, short circuit capacity, and system recovery capability. This must be independent of season and weather conditions as well. All of this can be provided by flexible firm gas capacity while also addressing the emerging need for highly dispatchable generation. So don't just take my word for it on the need for flexible generation. Global consultants and advanced ISOs around the world see the need for thermal flexibility. Bloomberg, there are several publications we can cite, but they claim that a flexible system is one that can respond to planned and unplanned variations in order to balance supply and demand over multiple time frames. IRENA claims that flexible generation will contribute to the long-term decarbonization. And the IEA even projects that in 2050, in the long-term future, thermal generation, while only representing a small portion of annual generation, represents the main source of seasonal flexibility in addition to hydropower, in systems with a high amount of variable renewable energy.
Thanks, Alex. And very related to what you have just mentioned, what are the main mechanisms to be in place to remunerate those services that you have just mentioned?
Okay, so thinking about ISOs, so large advanced systems around the world are procuring thermal flexibility with different mechanisms. In Brazil, their goal is to meet new demand with renewable generation, and they've actually structured new flexible capacity auctions that are specifically designed to procure thermal generation to balance the system across the entire year and through difficult climate challenges. In ERCOT, they have a target under the USA of reaching net zero by 2050. They're adding an ancillary service payment for flexible thermal capacity and subsidizing interest rates for projects that can be online in the short term. And then Australia, they have an 82% renewable energy target by 2030, and they've created a new market protection mechanism where risk and profit are shared across the generator matrix to be able to encourage both balancing and firm capacity, but also variable renewable energy capacity, which have different timelines and are exposed to different risks at different times across the day.
Great. Thanks, Alex. And final question that is very part of the current discussion in Chile. How or what are the impacts on tariffs? Final consumers, that they're represented in many, many ways in the local discussion in our market, such as important associations related to mining companies or big consumption consumers in terms of industrial consumption. They're very, very worried about the impacts in tariff. How do you see all this that we have talked in the final tariff of consumers?
Yes, so thanks, Analia, for the question. After thinking about all of what we talked about before, we can't speak to how system upgrade costs will be shared between the regulated and unregulated market, but our analysis shows that using flexible gas to manage capacity requirements of a high renewable system results in $683 million of annual savings beginning in 2032. This difference is primarily due to the large capex cost of investing in enough batteries to cover 24/7 power demand. And this savings will continue into the future by having a smaller generation mix. So lastly, Analia, there are some key actions that we can take to enable this change that we've talked about with all of my colleagues here. First is to finalize storage legislation that's in motion right now to incentivize a massive investment in storage in the near term. This will go a long way towards helping renewables integrate into the system. Next, it's to recognize that gas has a role to play in the Chilean power system, and recognizing that role is important to be able to enable it, to enable investment and incentivize investment in the right kind of gas, which would be flexible gas. The flexible gas has different attributes to offer to the system, but they're really encapsulated in these 3 points here. The ability to start quickly to provide energy on low renewable production days, the efficiency requirement to be able to supply energy at 24/7 all the time, and the ability to black start in the event of a blackout or a system failure.
Okay, so we are moving to last but not least to the final comments on this study that Varsila and all the members of the team have just walked through us. Thanks, Yusi, for disclosure. We have talked about the study. We have talked about the issues that are probably the main aspects to be part of the discussion, not only in 2024, but probably in the following years, thinking about a long-term discussion on decarbonization of our electrical system. So as a final remark, can you, in a very simple way, summarize the key ideas of the study that you have presented today to have, this big picture of the main aspects of this study? Please, Jussi.
Thanks, Analia. My pleasure, really. as a summary, I would like to point out two things. The first one is that there is a way out of the crisis for Chile. And to get there, Chile needs to close down 2.5 gigawatts of coal as soon as possible. This will increase the flexibility limit of the power system. But before we can do that, we need to add a lot of storage. We need to add some new flexible gas generation. We need to add some synchronous condensers. And when closing down those coal plants, we need to take the existing gas fleet into active use during the nights. These actions will not only solve the crisis, but they actually provide very positive impacts. Firstly, they have a major impact on the carbon emissions of the Chilean power system, going down from around 20 megatons a year to 6 megatons a year. So that's a remarkable step. And of course, coal is behind those emissions. And when you close them down, emissions go down. And contradictory to what you might think, the variable generation cost will not go up. Actually, they will go down about $400 million per year as less fuel is being used. So after doing this, you are then ready to add more renewables rapidly. That's the third benefit. And I said I will talk about two things as a summary. The second is that before Chile can really go forward, Chile needs to make an important road choice regarding the role of gas during the transition. Today, the policy is more or less that all fuels have to go, gas, coal, whatever, and as soon as possible. We have shown that other countries are really utilizing flexible gas power plants to speed up the transition, and that there are clear benefits of doing this for Chile. Firstly, $10 billion investment saving on the fully decarbonized power system. And this is because this firm gas capacity strongly reduces the necessary overbuild of the renewables and the storage. The security of supply will improve as the system operator can operate these flexible power plants at any time for as long as he needs. The outcome of using gas as a transition fuel is the same as without it, totally decarbonized power. And finally, you might not have thought that the power system with that firm flexible generation capacity using gas during transition and converting those plants then to use sustainable fuels later on provides actually reliable green power with $680 million lower generation cost per year after the decarbonization. So this is really a system that is more efficient than the system with only wind, solar, hydro, and storage. So my final question here is that why would Chile not do it?
So, many thanks to you all for this enlightening talk. We have walked through many interesting issues on the Chilean electrical system, defossilization, and emission reduction, which will surely be part of the energy political and technical agenda on 2024 and the following years. Thanks, Priscilla, for sharing your view and data. Since, as Lord Kelvin once said, if you cannot measure it, you cannot improve it. Thanks and goodbye.